Yeah, it's my great pleasure to be here to talk about my work on the Triton programming language in front of such a big audience. So what I'd really like to talk about today is the motivations behind Triton, the reason why it exists, also a little bit of how it works. So yeah, first of all, why did I feel the need to create a new language in the first place? There's already a lot of things out there. So I start with a little bit of background about myself. I spent most of my early years, as Vamsi said, developing code generators for OpenCL. So in 2011, for like about 3 years, I was a contributor for like the VNSA library, which was an HPC library using OpenCL. And I actually started using AMD GPUs way back then, and back then it was like called the Tahiti GPU, for those of you who remember. The GPUs were named after like tropical islands. Then in 2014, I had an internship at AMD also, during which I used like Hawaii GPU. And then I did like a PhD, during which I still did matrix multiplication auto-tuners. I use like some NVIDIA hardware, but also use like the Fiji Fury series of GPUs. And there's a bit of a theme here that like I've been basically for like 6 years, I was doing like matrix multiplication auto-tuners. And I think I got like a little bit crazy at some point. And it was not a very fun experience. So I took a step back and I thought, okay, like CUDA, OpenCL, HIP, or whatever, this kind of language, they're great. They give you like a lot of flexibility, but this comes almost always at the cost of simplicity. So the good thing about them is they have like very high optimization potential. So what I mean by that is you can always spend more time and engineering effort to get better performance. And in some cases, that's really great. You can go very, very down to the bare metal and optimize your computations and schedule them almost optimally. It's also like very flexible. So if at some point you discover your application could get some speed up by using, I don't know, like a tree or like a linked list or like some data structure, then you can also do that. It's going to take some time. It's not going to be fun, but you can do that. But obviously, the downside with that is very low research iteration speed. And productivity is very low. And this is why I spent 6 years working on the same workload, which is MATMUL, because productivity was abysmal. And every time new hardware came out, I had to like port all my code to the new hardware to make it work efficiently again. And after like 2 or 3 times doing that, I couldn't take it anymore. And obviously, like you have more code and you have more lines of code, and therefore you have larger surface areas for bugs. So in this kind of cases, when you first write your code, you think you won't have any bugs, but when you're done writing it, you have lots of bugs, and in CUDA, you tend to have more. So then I waited a bit, and I thought, okay, what exists out there that also serves like similar purpose? And I found like graph compilers. Graph compilers are more giving you like simplicity at the cost of flexibility. So it's kind of the other way around. So the main advantage is you have very high iteration speed for research. So you can prototype some ideas like very, very quickly, like sometimes in a day. And because you have less code, you just have less surface areas for bugs. Obviously, the downside is, on the other hand, you have like very low optimization potential. So you write your code, and if it's not fast enough, usually there's nothing you can do. Like you just ping the compiler people and hope that they will fix the problems. Obviously, there's also other problems around flexibility. So I mentioned before that you might want to use data structures that are more complicated than tensors to get the best performance out of your applications. Well, in graph compilers, you cannot always do that. So then I thought, okay, maybe we can sort of like meet each other in the middle and have a language that sort of like is halfway on like both the flexibility and the maintainability and performance perspective. So Triton basically is aimed to be like simpler than HIP and CUDA, but also more expressive than graph compilers. So the idea is what would take you like weeks or months to do in CUDA or HIP, you'll be able to do it in, let's say, a few days in Triton, or a few weeks at the very most. So like some colleagues of mine have said it's about like a 5x increase in their productivity. Obviously, another good advantage is portability and maintainability. So whenever there's a new GPU that comes out, you don't need to rewrite your entire stack, and that's nice. You get performance that's good. It's going to be at least as fast as Torch Inductor because Torch Inductor generates Triton, and it's a lot more flexible. So you can implement like custom data structure. You have like pointers, and you can support like complex indirections in your kernels. So that's all good, but then obviously I don't want to oversell the thing. And the disadvantage of Triton, a more pessimistic way to look at it is, okay, now you're less expressive than HIP and CUDA, and you're more complicated than graph compilers. And that's very fair. So you can do in days what would take you maybe hours to do in Torch or XLA. It's portable and maintainable, but only between GPUs, contrary to things like XLA or Torch again. In terms of performance, it's good, but it's always going to be upper bounded by lower level languages like HIP and CUDA. And in terms of flexibility, I think it's still like possible to like, if you want like thread level control of like your data structures, you cannot do that. So that's to set the stage for Triton and explain like the motivations behind this. And now I'm going to talk a little bit about like the development timeline because it's also important to contextualize this. So the first thing I did is in 2019, I was doing my PhD. I was very focused on making the whole thing just publishable. So I presented it at a conference. Then I interned at OpenAI in 2019. That was like a long time ago, and I worked on Triton there. Then a year later, I was focused on making Triton useful. And it's whenever you write a piece of software, it's always very hard to define what usefulness means and how to quantify it. So my measure for me, just how useful is it for OpenAI and how wide the adoption is within OpenAI. So I set myself to write all the GPT-4 kernels using Triton, modified the compiler a lot, broke the compiler a ton, added 1 million lines of technical debt, not really 1 million, but a lot of technical debt. And eventually this led to a complete rewrite of the whole backend, which was more focused about Triton making maintainable. And the days didn't get updated, but over the past few years, I was really focused on making Triton more portable, and that's also part of why I'm here, is because now we have really good support for MI250 and MI300, which I will talk about a little bit more later. So then now, you might wonder, okay, I talked about this Triton thing, but you may not have heard of it before, not really clear what it is. So the rough machine model of Triton is you have your GPU that's comprised of your typical like off-chip memory, that's DRAM or HBM. Then on the chip that talks to the HBM, you have all your cores, and each core has like some amount of like static RAM, and that's very fast but very expensive, so you don't have much of it. And the way Triton works is you're going to program to run programs on each cores individually. And this is very similar to CUDA, except that in lower level languages, you have to worry about what's happening within the cores, like what's going on with like the way the threads are scheduled. In Triton, there's none of that. Everything you see is there's like this big core that can run tensor operations. And usually, maybe like more concretely, what that means is users will define tensors, which, as you all know, are just like blocks of data, but they will define them in the SRAM of the chip instead of in the off-chip memory, like in Torch does. So if you're writing a Torch program and you do like a Torch tensor or something, the tensor will actually live like very, very far from the compute of your chip. And it means that every time you're going to want to do something on this tensor, it's going to be very expensive. And this is why you have all these compilers that do fusion for you to try to minimize that. In Triton, the tensors that you create actually live like on the core itself. So every operation that you do on the tensors, they're very cheap. But then it means that it's more complicated because then you program each core individually and you need to make sure they can talk to them and synchronize if needed. And there's like some quality of like features of Triton that are nice, and one of them is it's embedded in Python. So if you're used to writing Python, like Triton just like piggybacks into the syntax of the language, and you have a custom way to like visit the AST of of the program and generate our IR from it, and so on. It's very similar to NumPy, if you've heard of it. Does the same thing. A characteristic of Triton is you have pointers. So when you're using Torch and you write your Torch tensors, one thing you may have noticed is you cannot have tensors of pointers. It's just like not a thing in Torch. But obviously in Triton you need that, because if you want to access off-chip memory because your tensors are only in the SRAM, then you're going to want to have tensors of pointers that point to the off-chip memory and dereference that and bring the data this way to the chip. And there's some additional constraints of Triton that are not fundamental, but are just choices we made to make our life easier as developers. And one of those, probably the biggest one, is each Triton tensor must have a number of elements that's the power of 2. So concretely, if I had to give some examples of Triton, I would start with vector addition. So I'll just focus on a very simple vector addition kernel that runs on a single core of your GPU that doesn't do any bounce shaking or none of that. So the first thing you want to do is you want to import your Triton language library and Triton, and then you're going to create a Torch function that's going to take pointer arguments for every tensor that it operates on, and you just annotate it with the decorator, as I mentioned. This is the way to tell Triton or like compile that particular function. Then you create like a tensor of offset, because remember the goal here is create at a high level, create a tensor of pointers that point to the elements in the HBM, difference that to bring the values on chip, then do operations on chip, and then write them back. So you want to create these tensors of pointers. So you can create like a range of values from 0 to 1K, and then you can create your tensor of pointers by setting the initial, offsetting your initial pointer arguments with these offsets. And then you can do tl.load, which will load the values and bring them from the off-chip memory to the core itself, where any sort of processing is super efficient and super fast. And then once you're there, you're going to do your computations. Here it's just an addition. And then you're going to write back. So you use your pointers to the destination addresses to write back your data element-wise. And then when you have that, you can test it by creating a random tensor and executing it, executing your function. When you run your function, you need to provide a grid, which is essentially how many programs are in parallel, because remember your GPU has more than one core, so you might want to execute replicas of this program on many different cores at the same time. And now if you wanted to do something a little bit more complicated, what you could do is you could like have like an additional way to index the tensors that depends on the ID of the core. So now when you launch your add kernel, you provide a grid that's not just like one single program, but however many program is needed to process your entire tensor if each program handles like 1,000 elements. And in your kernel, the only thing you have to change is you have to modify the way you compute the pointers so that each program only accesses pointers that start at the index that it processes. And then when you load your data, you also need to mask it so that it doesn't access memory out of bounds. And then in the slide before, I hard-coded the number of elements processed by each core to like 1,000, but you can do anything else that you want there as long as it's a power of 2. So another way to sort of tune that is to add an argument that's what we call a constant expression to the program, and therefore this way you can specify a block size and change your kernel so that it only operates on that block size. And then your grid then also depends on the block size. And if you do that, you can see that at least on vector addition, this very simple kernel, you can get like pretty good performance, which is achieving the peak memory bandwidth of the chip. Now, just to spend like a couple of minutes on a slightly more complicated example. So if you had a matrix multiplication, the way you'd want to do it is you want to say, well, I'm going to have each core process a tile of the output, and then in a loop, I'm going to like load tiles for my left-hand side, load tiles for my right-hand side, multiply the two ties together and sort of like accumulate that into some values, some tensor on chip that I then write back after the loop. So without too much details, if you do that and if you implement it in this very straightforward way without like any fancy trick, you can actually get like a pretty good performance on matrix multiplication. So you can see again that it's comparable to like the most hand-optimized kernel that's been written by AMD for matrix implications. So then it's good in the abstract, but is it actually useful? I said at the beginning, one of my main goals with Triton was to make it useful for OpenAI. And yeah, was it actually helpful? So I've been at OpenAI for a long time, and I've seen the company grow like almost 20x basically in my time here. And one of my big concerns and worry when I joined is like, oh my God, as the number of researchers grows and the number of GPUs that we support grows, the work I'm going to have to do is going to grow like linearly with that. And there's only like 24 hours in a day, so eventually I'm not going to sleep anymore. Then I'm just not going to have enough time. So then the good thing with Triton is you sort of change the equation in a way that the maintenance burden for all these kernels is more like an upfront cost that you have to pay for the compiler work. But then once the compiler works, researchers can sort of self-serve and write their own kernels or modify existing kernels for their own needs. And just doing that has like very, very significantly reduced the amount of work that the kernels team had to do at OpenAI. Obviously, like one counter argument is you can just hire more, and I think many companies also operate this way. Is let's just build bigger teams and like scale horizontally. Like let's have like a team for one vendor, one GPU vendor, another team for another GPU vendors. But this doesn't really scale well because all you're doing is really just like changing the slope of the curve, or like the y-intercept if you hire more for compiler developers. Another thing that I think Triton helped a lot with is like reducing technical debt. So I'm sure all the developers in this room know that like at the beginning of every project, everything is wonderful and very maintainable. And then as the thing grows, it becomes a mess. And then eventually like you want to add small features and it takes a very, very long time to even like add tiny features, and it's frustrating for everyone. And obviously the high level language you use, the less of an issue it becomes because the less lines of code you have, and also the easier it is to fit like entire programs in your head. So in Triton, like Triton at OpenAI has been very, very helpful with that, just allowing us to tackle this upfront. And now whenever we want to change things in our kernels, it's not like a monumental task that frustrates the entire team. So I think that's been another big success for us. And another thing that I think Triton allows you is getting like very good performance more quickly. So I think the way I like to think about Triton is it's not going to be like a silver bullet that's going to solve all your problems. I don't want to make like any of this promise, but like the whole premise of Triton is like you're going to get like higher return on investment quickly. But then you have these pitfalls that as you spend more and more time on that, you're going to plateau at a lower performance level than you could get if you used a lower level language. So usually that's how I like to think about that. And what I've also learned in my time at OpenAI is performance is important, but what's even more important than performance is being able to move quickly and adapt to new architectures that come out, to new requirements from products or from research. And Triton has allowed us to do that. So in conclusion, again, I don't want to sell Triton as this wonderful thing you should go and use today. You may or may not like it. I think it's all a matter of trade-off. There's things that Triton do well. There's things that it doesn't do well. That there's places where it's the right thing to use, where it's not the right thing to use. And Triton, at the end of the day, is just like a programming language that's like more of a medium level of abstraction versus like what you'd use if you were doing CUDA or HIP or Torch, that's higher level. And the main goal of Triton here is really to trade off performance for productivity. So when you're using Triton, you're basically saying, I'm going to get a little bit worse performance in the general case, but I'm going to be much more productive. Obviously, like for very specific and common workloads like matrix replication, we can reclaim the performance and optimize the compiler well enough so that it's not a problem. But in the general case, if you think about a new research idea that you have or something, Triton is not going to be as efficient as your lower level language, but it's going to make you more productive. Triton has been like very critical in allowing OpenAI to scale kernel development, as we've grown for like 100 employees to, I don't even know how many we are, but like between 1 and 2,000. And I think it's been very critical to allow us to keep doing research productively and efficiently. It's made like everyone much more productive, essentially. And another big selling point of Triton, and I think maybe like particularly relevant to the audience here, is it's very portable across different GPU architectures. So all the performance numbers I showed, you get roughly the same on NVIDIA GPUs, and we know many people, including us, who've been able to write kernels that are portable and get good performance across like different GPU vendors. Okay, I think that's it for me.